So now that you've learned a bit what an async task class is, the framework that's used to implement it, the black box and white box dimensions or features in an async task framework, you saw a quick walkthrough of the implementation of the async task. Let's now go ahead and understand the usage considerations for an async task. So here's a couple things to remember. The first thing to remember, async task, its primary purpose in life is to allow computations to run in the background and to make it fairly simple to communicate from the foreground to the background thread, or more specifically from the background thread to the UI thread or the foreground thread. That's the main thing it does. It makes that communication very simple. And in particular, it has these hook methods on pre-execute, on progress update, on post-execute, and these always run in the context of the UI thread. And the framework's purpose is to make that easy to do. These methods are, and the pieces of the async task framework that we just looked at, they're strongly connected in the sense that it's got a very simple surface area. You just extend, and then it keeps track of all these things, and you don't have to know about the details of how it all works, which is cool. So you just say execute, give it some parameter or parameters, and it goes ahead and, as we saw, makes those parameters run in a thread from a background executor. And then if you want to publish the progress, they'll end up showing up in the UI thread. If you want to do on post-execute, that'll show up in the UI thread. And unlike the Hammer framework, which is used to build this thing internally, by the way, you don't have to know anything about handlers, messages, runnables, threads. All that stuff is abstracted away from you. So it's hidden, and you just have to focus on your logic. Async task embodies the key characteristics of a framework. What were those characteristics? Inversion of control. In other words, it owns the background thread. It actually owns the thread. Once you call execute, it owns the computations and the callbacks. And those are all done by callbacks that are made at the right time in the right context. It has a bunch of domain-specific structure and functionality. All the stuff that we see here, executors and message queues and handlers and all that good stuff, those are all from the domain of concurrent programming. And it implements a semi-complete portion of an application where a lot of the code is done for you. Those 676 lines of code are given out of the box, so you don't have to re-implement them. And instead, you simply come along and override whatever method or methods you find important for what you're doing. So certainly do in background, but could be other methods as well, like on post-execute and so on. Async task is cool because it has elements of both black box and white box frameworks. So its hook methods, like do in background or on pre-execute, on post-execute, etc., those are all elements of white box framework because we have to override them. So we have to know about the fact that we have to subclass, and we have to know that those methods are called at the right time. Its executor strategy is an element of a black box framework because you give it an executor instance that's called at the right time in the sequence of the execute on executor method. And there are trade-offs between these things. And this is really important to understand. You'll use frameworks a lot throughout your careers, an enormous amount throughout your careers. You might or might not build many frameworks. People are most typically users of frameworks rather than implementers of frameworks. I like to sort of think of it like a funnel or an upside-down pyramid, right? There are very few people who have to build a framework, so they're kind of at the bottom, the small part. But there are lots and lots of people who will use it if it's a successful framework. So most people will be users. So thinking about this both from a user point of view and a developer of framework point of view, white box frameworks tend to be fairly easy to develop. You just have to define a bunch of subclasses or superclasses that you subclass and override certain methods. But they're harder to use because you have to know about all these hook methods and when they get called back and the context in which they get called back and so on. In contrast, black box frameworks are generally harder to develop because you have to anticipate a lot more of the common use cases. You have to figure out how to come up with the plug-in architecture in order to have these black box interfaces. But they're easier to use because you just have to give instances of things to them, and you don't have to subclass, typically. You just have to say, here's an instance of this. Go do something with it. So it's a bit more like a plugin, if you're familiar with the concept of a plugin, which we use all the time in browsers and other applications. There's a bunch of gang of 4 patterns that are in AsyncTask. The most obvious one is template method. Remember, template method defines an algorithm or the skeleton of an algorithm in a method called the template method. And then it defers some parts of the algorithm's steps to subclasses or allows the subclasses to selectively override those steps by so-called primitive methods, or what I like to call hook methods. So that's what template method does, and that's used extensively. You've got all these methods in AsyncTask that can be overridden, and you can override some of them if you so choose in order to be able to customize the behavior of the AsyncTask using the framework. So that's one set of things. And as you can see here, when you call execute, which is the template method in the template method pattern, then that'll end up calling back on pre-execute and on post-execute at the right point in time in the UI thread, and it'll call do in background at the right point of time in the background thread. So that's kind of template method. Strategy is used to pass in the executor strategy to the execute on the executor method. So you pass in a strategy, and that's typically a strategy object that you pass in there. And then, if you really think about it, the facade pattern is also being used to simplify access to all the moving parts that go into the implementation of the AsyncTask framework, which, of course, also includes the executor framework, too. So facade is a pattern that gets used over and over again whenever you try to take a complicated set of classes and their interactions and then provide a smaller surface area, so you only have to focus on a few key entry points or hook methods, which is the way AsyncTask works. AsyncTask also uses a bunch of POSA patterns, pattern-oriented software architecture patterns, such as the ones from my book, which came out a long time ago, but still relevant. The most obvious one is half sync, half async. And this is a really cool pattern. You can either read it in the book or you can get it from the website here. And what that allows you to do, the pattern allows you to be able to separate between things that run synchronously in threads and things that run asynchronously without blocking. So you have sort of the asynchronous non-blocking layer, and you have the synchronous blocking layer. And the way it works in the async task is you make these calls from the UI thread, which, as you recall, can't block. And it basically queues them up into a blocking queue that's then used to service background threads that process the stuff in the background. It also uses the concept of pooling, which is another pattern, which has a pool of threads. That's what the executor framework is providing for you. So you can take a look at the pooling pattern. And these are just other common POSA patterns. There are a number of traps and pitfalls with AsyncTask. Some of these are easily worked around. Others of them are more subtle. They all have workarounds. You just have to know what you're doing. And it often helps to have patterns to help you work around the traps and pitfalls. So one of the traps and pitfalls is that cancellation is voluntary, just like thread interrupt is. So if you cancel an async task and the async task's do in background method never checks to see if it's been canceled, then cancellation won't actually do anything. It'll just make you feel like you did something. But it won't actually cancel anything. Dependency on activities. So if you think about the purpose of async task in the context of Android, it's usually to allow an activity, which is how you interact with the user, to communicate with a computation that runs in the background. And if you're not careful, you can end up with so-called memory leaks if there are so-called strong references to the enclosing activity. So you can have these leaks. And so there's a bunch of tricks to work around that, basically having to do with using weak references. You can also, if you're not careful, when you rotate your phone, if you haven't designed things cleverly with the AsyncTask, restore state stuff that I showed you, then you can end up having the connection between the async task and the activity broken, which means the async task is doing nothing useful because it can't get the results back to the new activity that was just created. So you have to be clever about that. And then there's also some really weird quirks having to do with portability issues. So over time, the designers of Android have changed the semantics of async task by default. So in the early versions of Android, this goes back 10 years or so, when we had the donut release, the tasks were executed serially, like they are now. And at some point during the gingerbread period, thank you, sir, appreciate that. See ya. During the gingerbread time frame, they changed it so that async tasks ran in parallel in the background, which made everything run faster, but it broke all kinds of code where people didn't know how to do synchronization. So then, starting with the Honeycomb release until now, they changed it back. So they added this, or they allow you to be able to call execute on executor. So the way around this, if you really want to have consistent semantics, just use execute on executor all the time and pass in the semantic that you want based on the executor parameter that you pass to it. This is a good example of how, when infrastructure changes, you have to be prepared to handle those effects on your application code. Some of these problems can be addressed by using the right types of patterns. So there's a cool pattern called ModelViewPresenter, which can be used to make your code impervious to rotation changes and disconnect the dependencies on activities. That's a cool approach. If you look at the code I wrote that's in the GCD example, you see that that's what it does. And then things like cancellations and portability can be addressed by understanding other Android patterns and APIs. So cancellation is just always voluntary in Java-based systems. Portability can be handled by knowing how to use these extra methods like execute on executor. Async task is very, very heavily used throughout Android, used all over the place. Oddly enough, the on-progress update method is not very widely used. There are some places it is used, but it's not as widely used as the framework itself. And that is the end of that.